section 1.4, we're going to look at different factors that impact the strength of evidence, and one of those is whether you have a one-sided or a two-sided test. So this is from a study where the researchers wondered whether men or women are more likely to say I love you first. So they looked at 47 heterosexual couples. For 7 of those, the people actually couldn't agree on who had said I love you first, so they threw those couples out. But for 28 out of the 40 couples who agreed, the man said I love you before the woman did. So the observational units in this study are actually the couples, right? Because we're measuring something about the couple who said I love you first. That applies to the couple, not to any of the individual people in the couples. We have 40 couples in our sample, so our sample size n equals 40. The variable that we're measuring is who said I love you first. So the man or the woman in this couple, I'm going to start abbreviating I love you so I don't have to write it a million times. We want to know the long run proportion, or the true proportion. So pi in this case is going to be the true proportion of couples. So we'll stick with success defined in terms of men, since that's how it was in the question. The true proportion of couples where the man says I love you first. We're going to use the 3S strategy here. So starting with the sample proportion, we've got 28 out of 40, and that comes out to be 0.7. So let's state our hypotheses here. Our null hypothesis would be that in the long run, that it really is balanced, right? That it just ended up a little bit higher in this sample just by chance, but actually women and men are equally likely to say I love you first. That would be our null hypothesis. Equally likely to say I love you first. So then what about the alternative? Usually when we're writing the alternative, we're going to pick some kind of inequality and we're going to base it on the question. But this just says whether men or women are more likely to say I love you first. There's no speculation in the question about which group it's going to be. So in this case, we don't really know if it should be greater or less, and so we're just going to use not equal in our alternative. So I'm going to abbreviate sort of and just say the alternative is that women and men are not equally likely to say I love you first. So at the simulate step, we want to know what values of p hat would occur if the null hypothesis were true. And since the null hypothesis is about being equally likely, and because the null hypothesis is about being equally likely, we can just set this up with a coin flip. So I'm going to say heads is the man says I love you first, and tails is the woman says I love you first. We have a sample size of 40, so we're going to do 40 coin flips in each set. Every time we want to record the same statistic that we used to describe the original sample, so we're going to record the sample proportion and repeat this many times. So I'm going back to my one proportion applet here. I'm changing the sample size to 40 and drawing my samples. I don't really want the normal approximation. And the value that I'll put in, my statistic, is 0.7. Okay, so we can see here a value of 0.7 seems pretty unlikely, right? Happening less than 1% of the time if the null hypothesis were actually true. But notice right now we're only looking at the values where men say I love you first more than 70% of the time. We also want to consider the possibility that women say I love you first more than 70% of the time. So we kind of have to go the same direction on the other side. So if we click here where it says two-sided, this is going to shade not only greater than 0.7, but also less than 0.3. And because this distribution was pretty symmetrical, it's going to pretty much double the p-value. So it may help here to come back to our definition of a p-value, the probability of getting results as or more extreme as the observed statistic if the null hypothesis were true. So notice this language, as or more extreme. So this allows that it could be greater than, less, or it could be in either direction, right? It could be more extreme in either direction. So this is actually why we call this a two-sided test, because when we go to find our p-value, we find our sample statistic, p hat equals 0.7, and we shade everything in that direction. So in this particular example, that represents more than 70% men, but we also have to shade on the other side. We also have to have 0.3 and shade everything to the left. So in this particular example, that represents more than 70% women, right? Because if you have less than 30% men, then you have to have more than 70% women, since everybody in this study identified as one or the other. So we count both of those in our p-value, and we counted on both sides. In this example, we ended up getting 0.0173. So this gives us strong evidence against the null and for the alternative. So strong evidence that men and women are not equally likely, since that's our alternative, to say I love you first. So one other thing I wanted to mention here is that one-sided versus two-sided, that only comes up when you're dealing with p-values. The z-statistic will actually be the same for one- and two-sided tests, so that's just not something that the z-statistic takes into account. So that's why I said in a previous video that sometimes the guidelines for p-values and the guidelines for z-statistics contradict each other, and this is why, because p-values take into account one versus two-sided hypotheses, and z-statistics don't.